you take theta, theta, this is in function of r, starting, let's say, from 0. In fact, this is starting not from 0, but it's starting from r up and going to r tip. So we are reducing, maybe r up is there, r up is there, rt is there. Maybe you are reducing like this, linearly. Maybe you are reducing like this, hyperbolically. There are different solutions with here theta h, with here theta h, and here theta tip. So that is much smaller. How can you do that? Increasing, it's not possible. You have built the blade like this. The blade is this one. You cannot change anymore the shape of the blade. But what can you do? You can put the blade, if it's linear decrease of theta in function of h, you can put the blade like this. Or you can put the blade like this. So you have here an addition of a certain theta that we call theta general, and you have here the decrease of a certain theta general. And you see that in fact the theta has a certain equation. It's a theta general that is depending on how you are fixing the blade in this direction. So you can rotate the blade like this in this direction, and then you have a certain theta multiplied by r with a negative sign, because you see that it's decreasing, that you can call a theta, I don't know, c if you want, or theta 0, I don't know how you want to call it. And you see that you have built the blade like this. So this is the twist of the blade, and you have a variable part here, a variable part that will be chosen by the pilot before the flight, if it's a system without a CSU, or that will be changed by the CSU during the working. So the CSU will measure the rotational speed. If he feels that the rotational speed is decreasing, what will do the CSU? It will increase the theta by a certain angle everywhere along the full radius. And if he feels that theta is increasing, if he feels that theta is increasing, he will go up, and if he feels that theta is decreasing, he will go down. So this is the CSU. So he measures the rotational speed of the propeller and try to have a constant value by acting on a variable part of the equation of theta, which is called the generic or general or collective value. There are different names. Increasing it if the rotational speed tends to increase, yes, and decreasing it if the rotational speed, decreasing it if the rotational speed tends to decrease. Okay, so this is a very important, let's say, feature or component of a turbopropulsor. And so we see that in fact the turbopropulsor is a difficult animal because this angle theta is, let's say, influencing a lot of parameters, is influencing the angle of attack and influencing the distribution of the force TH, making that we select a theta that is decreasing with R, and also theta is used in the CSU with a variable term that is in front here that can increase or decrease. So increase when you will have the trend to have omega that is increasing, to avoid that omega is increasing, and with a negative value here, a negative value, when you will have the trend that omega would be decreasing, to avoid that omega would be decreasing. So if omega is decreasing, as a trend to decrease, you decrease the value to re-increase thanks to that the omega, and if it tends to increase, you increase it so that it tends to decrease again. Okay? And this theta is also closely related with the evolution of eta h. So this pitch angle or pitch law of the propeller is really a very important parameter. And don't forget this double row system that we have there, that is a key parameter. Now, there is something else that we need to discuss when speaking about turboprop. This is this problem of having two parameters to express the performance. A parameter that is linked with the power and a parameter that is linked with the force. In fact, it will be very easily solved. So the problem is rather easily solved, because if you speak in force, you have TH added with the resulting force, and this is making a total force. If you speak in force, the problem is very easily, let's say, solved. But it's a bit strange to speak in force, because the main part of this total thrust is coming from TH. TH is much larger than the F residual, and TH is created by a power. So it's a bit strange that we would solve the problem as easily as that. We need mainly to understand the problem from a power point of view, and not to solve it from a thrust point of view. But in fact, we can do both. We can take the both paths. And what will make the link, in fact, what will make the link, this is eta h. Because eta h, this is equal to TH multiplied by VA divided by PM. That we call also the SHP, as I said. Or P, if you want, the power just before the, on the shaft of the propeller, just before the propeller. And by using this eta h, in fact, what can we do also? We can say that we can write also that eta h is used in order to transform the residual thrust into a power. How can that be done? This is like you change the engine we have here, where V jet would become equal to VA, so there is no residual thrust, and this residual thrust, you transform it into a force that you have here, that would be created by a P that is a bit higher than PM. And how much higher than PM? What you could call here a P residual or something like this. And this P residual is not existing, but this would replace the power created by the F residual through the exhaust nozzle. And that would be equal to, very easily, F residual multiplied by VA divided by eta h. And so you see that you can also write this engine in this way. You can write this engine as PM plus this F residual multiplied by VA divided by eta h. And so you can write the engine as a thrust engine with this, or as a power engine with this, and that would create a power that is higher than PM, that we call sometimes PM equivalent. This term is sometimes called the SHP, and at that time we call that the equivalent SHP. The equivalent SHP is the SHP you have really here, plus a term that would potentially come from the F residual that would be 0, and that would be added to this power. And this, of course, you see, as Pm is equal to Th multiplied by Va divided by eta H plus F residual multiplied by Va divided by eta H, you see that it can be written as Th plus F residual multiplied by Va divided by eta H, and this is equal to T total. And so you see that you have a total equivalence in this way to write the performance of the propeller, of the turboprop, by speaking about the turboprop as, in fact, a turbofan. So when you express a problem like this, you replace, let's say, the turboprop by a turbofan, where you have as a thrust T total, or when you are speaking like this, with this equal to T total multiplied by Va divided by eta H, or that you call T total, you can also call eta H as T total multiplied by Va divided by the ESHP. And here you speak about a power engine, here you speak about a turbofan engine. It's the same engine, it's just a different way to express the propulsive power that is used to propel the aircraft, coming from a propeller with this term, or also expressed this way, this is the same equation, or expressed in this way. And why do I use this way to express the turboprop? This is because I have like this shown that the turboprop can be seen as a power engine or can be seen as a thrust engine, so a turbofan. And why? What is my objective? What is my objective in explaining that? My objective is to use the parameters of the turbofan. And mainly to use which parameter of the turbofan? The bypass ratio. Why? Because I know that the bypass ratio is the most important parameter that we have introduced in this course. And by showing you the similarity between a turboprop and a turbofan, I am able to say what the turboprop is an ultra high bypass ratio